Hello everyone, let's talk about 4.2 in Calculus 1, which is area approximation, sigma notation, and limits and how they kind of work together. But before we talk about area approximation, we need the sigma notation first. And this is a way to represent both finite and infinite sums. So sigma notation says the sum of n terms, a1, a2, a3, all the way to an, however many you're adding, can be written as the sum from I equals 1 to n of ai. So ai represents each term, each numbered term, all the way up to the last one in your list. So this represents where you're starting and where you're ending. This is called sigma notation because this is the Greek symbol sigma. So I is technically referred to as the index of summation, and ai is the ith term, and the upper and lower bounds of summation are the upper bound being n and the lower bound being 1, and that's where they will be placed. So some examples of this in action are the sum from I equals 1 to 6 of I, which really just means you're plugging in 1, 2, 3, 4, 5, and 6, and you're adding them all together because it's a sum. Here are some other ones, but the idea here is, especially looking at A and B, you can notice that the same sum can be represented in two different ways, and so sigma notation can be kind of interesting. E and F is something you can pay particular interest to as well, because those are things that represent skills you will be able to use. And by that I mean, you notice on E that when we have 1 over n times k squared plus 1, and k is the one moving from 1 to n, that 1 over n just sits in front of each of the terms, and what ends up happening is because n is not affected by k in particular here, it ends up being able to be moved outside of the summation. So that's just something to keep an eye on. Like I said, if there's a constant that's not affected by the summations variable in particular, it can be moved out front. And if you have two things added or subtracted together behind a sum, then they can be split into two summations and then add the answers together. Now, obviously, if these have any significant number of terms, it's going to be unpleasant to do these by hand. Even the one where there's only 6 terms, it's going to take you a while to write out the terms and then add them all together. So what we've got here is some shortcuts for finding the sums for some common terms, particularly some of the polynomial terms like I squared, maybe I cubed. So if you're adding a constant over and over, let's say 2 was just sitting here and you were going from 1 to 10, obviously if you add 2 10 times, it's the equivalent of 2 times 10. The rest of the patterns, though, may be less obvious. The sum of I, where I is going up each time through n, the pattern here is n times n plus 1 over 2. So we can see by adding these together, 1 plus 2 plus 3, 6 plus 4, 10, 15, 21. But with n being 6, if we had just used this formula for I, it says 6 times 6 plus 1, so 7 divided by 2. 6 times 7 is 42, divided by 2 is 21. As you can see, that's the same sum that we've got there. And these are for I squared, n times n plus 1 times 2n plus 1 over 6. And then I cubed is n squared times n plus 1 squared over 4. And so that we can use these things to approximate sums that are just probably generally too annoying to deal with otherwise. So evaluate the following sums given in sigma notation for n equals 10, 100, or 1,000. So the first thing I want to do is recognize that the only thing affected by my summation is this I plus 1, so I can pull 1 over n squared out front, because it's just going to be whatever 1 over n squared is, times I plus 1. Well, this is I, this is 1. And of course, if two things are added together, I can split them. So 1 over n squared times the summation from I equals 1 to n of I, plus distribute the 1 over n squared times the summation of I equals 1 to n of 1. Now we know the pattern for I is n times n plus 1 over 2. And the pattern for 1 will just be whatever this constant is times n. So this is times n. And if I simplify this, here and n will cancel. So we'll have n plus 1 over 2n plus one of the n's cancels here, 1 over n. And then that gives you a simple formula for this thing that can be applied to each of these n's in particular. If I wanted a common denominator here, this would be 2 over 2n. And if I added those across, this is n plus 3 over 2n. So if I evaluated this at 10, 100, and 1,000, I can see at 10, it would be 13 over 20. At 100, looks like it'll be 103 over 200. And at 1,000, it will be 1,003 over 2,000. So if you can simplify the pattern, it becomes pretty easy to plug in the numbers. I will leave B for you to do. These are somewhat useful for now and to help us develop some concepts, but they become less useful later. So if we relate this to geometry, you probably wonder, how do we get a lot of our formulas for some of these shapes? Well, in Euclidean geometry, originally, the simplest type of shape was a rectangle. And so people often tell you that the formula for the area of a rectangle is base times height. But the truth is, when they were defining area, how much it takes place, they defined it for a rectangle first. So the definition for the area of the rectangle is the base times height. And that's nuance in many ways. But it was from that definition they developed many other definitions. For example, the triangle, you could find a triangle to be half of a rectangle, which is how that one came to be. And once you know triangles, you could break up many shapes into combinations of triangles to develop the area formulas for each of those. Now, for polygons, regions that aren't polygons, don't have a certain number of sides, slightly more difficult to establish. But what they did for things like a circle, for example, is they would take areas of shapes they knew and create a circumscribed and an inscribed shape. So circumscribed will be along the outside, inscribed will be that shape drawn on the inside, and if they can find the areas of the smaller and larger shapes, they can kind of approximate the area of, say, a circle. And the more sides you put on the shape, the more accurate this measurement became. So the same kind of idea can be used to approximate the area under a curve using rectangles. So let's say using 5 rectangles, show that the area to the right, like under this curve, is going to be between the lower estimation and kind of this upper estimation of the picture. So the first thing that we need to do is generally identify the width and the height. Now, looking at all of these, I know that the width is 2/5 for each one of these regions, but the height is just going to be the function evaluated for the first one on the right side. For the second one, it looks like it's evaluated on the left side. So for the first picture, A, what we're going to do is we're going to use sigma notation. I know that I have 5 rectangles, and each rectangle is width times height. I know my width is 2/5, but my height is changing, but it's the y value. And we're going to call this 2i over 5. This one will be actually b, because b starts at 1, 2, 3, 4, 5, whereas the one that's a starts on the left, the height. So we'll talk about how we deal with that in a second. Now, what is f of 2i over 5 in our function, negative x squared plus 5? Well, if this is our x, our actual width here from I equals 1 to 5 is negative 2i over 5 squared plus 5, because we're just replacing x with our 2i plus 5, and this is all multiplied by 2/5. And if I do this, using my previous approximations for how these work, what I'll notice is that this is, what, negative 4i squared over 25 plus 5 times 2/5. So this is the summation from I equals 1 to 5 of distributing the 2/5 will be negative 8i squared over 125, and the 5 times 2/5 will be plus 2. And if I use my sigma notation rules for I squared, etc., and what I can move out front, I know that using my rules, I can pull negative 8 over 125 out from I equals 1 to 5 of I squared, plus the integral, the summation from I equals 1 to 5 of 2. And using my I squared patterns, this will be negative 8 over 125th times the pattern for I squared on our first page was n times n plus 1 times 2n plus 1 over 6. And then for this one, it's just 2 times n. But my n here is 5. So this is negative 8 over 125 times, this will be 5 times 6 times 11 over 6 plus 10. And I notice the 6 over 6 will cancel. Then 5 over 125 can be reduced to 25. So I have negative 8 times 11, so negative 88 over 25, plus 10, which is 250 over 25, for a total of 162 over 25. So which one is this? This is one of my approximations of the size. How do I know which one it is versus the one that it's not? Again, I'm looking at f of 2i over 5 from 1 to 5, which means my first one is when I is 1. So if you're not sure which one you're doing, the first one is when I is 1. Which one of these heights is measured at 2/5? It's actually the right side of this. So this is the lower estimation, and as a decimal approximation, this is 6.48. The right side evaluates kind of the same exact one, but instead of going from 1 to 5, it kind of goes from 0 to 4 because it uses the left side. And the way that we deal with that is that instead of my I starting at 1, I can put an I minus 1 because it's starting at the left. And so from there, you can get kind of an approximation. It turns out the second one ends up being 8.08. So what we can say, though, is that if the part from A is 6.48, and the part from B, the larger estimation, is 8.08, we know that the actual area under this curve is between the two of them. So we can kind of say that the area is between 6.48 and 8.08, which gives us a kind of idea of where this area is. And we'll talk more about the applications of this in the next video.